Section 6.1, Properties of Exponents. We have several properties of exponents to discuss. The first one is a special exponent with an exponent of 0. Any time that you raise a non-zero number to the power of 0, which we may call the 0th power, it equals 1. And so you can see several examples here. 4 to the 0th is 1. Negative 3 to the 0th is 1. 1/3 to the 0th is 1. In fact, anytime you raise any number to the 0th, it equals 1, as long as a does not equal 0. That's a special case that I mentioned over here. 0 to the 0th power is undefined. It does not have a particular value. It's not positive, negative, 0. It's not 1. There's nothing we can give there for a final answer. So anytime you get 0 to the 0th, it's just undefined. In addition to 0 exponents, we could have negative exponents, which would be a different case than what we would expect from a normal exponent that's positive. And anytime we raise a non-zero number to a negative power, we end up getting a reciprocal and making the power into having a positive exponent. So you can see what we've done here is we've taken 4 to the negative second, and we've rewritten that as 1 over. That's kind of a big way that we end up with a reciprocal. 1 over 4 to the second. So I've taken the same expression I had here, but I've just changed the exponent to be from a negative 2 to a positive 2. And I've moved the 4 down into the denominator of a fraction. Since I had nothing left in my numerator, I left a 1 up top. Same thing would be true if I had a negative 3 being raised to the negative second power. I'd bring negative 3 entirely down to the denominator, negative 3, make my exponent of negative 2 into a positive 2, and use a 1 as a placeholder. Now, if what I am raising to a negative power is a fraction, I can just find the reciprocal of the fraction. And so 1/3, the reciprocal of that is 3 over 1, and that allows me to take my negative exponent, make it a positive exponent. Now, 3 over 1 I could actually reduce pretty easily to just 3. And so I can actually take the expression 1 over 3 to the negative 2 and reduce that just to be 3 squared, which is much, much easier. Once again, I mentioned a non-zero number. If I raise 0 to a negative exponent, I'm going to have something unfortunate happen. I end up with 1 over, so I'm using the reciprocal, and 0, and instead of having it to the negative second, I make it to the positive second. Now, I know that 0 to the second power, or 0 times 0, is just 0. But this leaves me to 1 over 0, which is something that is not doable in math. This is a value that we call undefined. Very similar to 0 to the 0th. This is not any number, not positive, not negative, not 0, not 1, not infinity. It's just an undefined value. Okay, now we have some general laws of exponents that you actually investigated in the explorations in class. This is just to formalize them and have them here as reference for you. If we assume that a is going to be a real number, and m and n are integers, they could be the same, they don't have to be, then these equations will hold true. For a product of powers, meaning multiplying two things together that have exponents, if the bases are the same, in this case both a, then I can add the exponents. And so what I do here is I have 4 to the 6th times 4 to the 3rd. I'm going to keep the base the same as 4, and I'm going to take my exponents and add them. 6 plus 3. So that's going to be 4 to the 9th, which is a whole bunch of 4s multiplied together. I don't need to put that all the way out and figure out what that number is. For something like that, it's going to be a very large number. A calculator is going to be the way to go for that. The next property is a quotient of powers. Quotient just means a division, which is often written as a fraction. And in this case, I have a to the m over a to the n, and all that I have to do instead of adding the exponents is subtract them. And I always take the top exponent and subtract the bottom exponent. So 4 to the 6th over 4 to the 3rd equals, I keep my exponent, my base, the same as 4, and then do 6 minus 3. And 6 minus 3 is 3. So I'm left with 4 to the 3rd. Certainly much easier to do out than 4 to the 9th. I think that actually ends up being 64, but that doesn't particularly matter. What matters is the property. Then we finally have power of a power, which is taking some exponential expression and raising it to another power. And all that I have to do there is multiply my exponents together. So 4 to the 6th to the 3rd becomes 4 to the 6th times 3, which means my exponent is going to become 18. Much larger than even my first one, 4 to the 9th. That number I would never ask you for the final answer because it would be kind of ridiculous. But those are 3 of the general properties. One thing just to be careful with, especially when dealing with the quotient of powers, but it applies to the other 2 as well, is if any of our exponents are negative, then it may result in subtracting a negative. As a quick example, so you can see what that likes, if you have 3 to the 2nd over, let's make that second look a little bit better there. If you have 3 to the 2nd over 3 to the negative 5th, that's going to become 3 to the 2 minus negative 5. Keep in mind that you're subtracting a negative there, and therefore you end up with 3 to the 2 plus 5, which would be 3 to the 7th. So just something to keep in mind going forward. It's something that can often be tricky when you're trying to simplify those problems. Just continuing with some general laws, we're going to have a and b be real numbers, and we're going to have m be an integer. Now, one thing to keep in mind here is that we have different options for a and b. They can be fractions, they can be decimals, they can be negatives, positives, 0, whatever, in most cases. But m has to be an integer, so no fractions or decimals as our exponents. First thing is a power of a product, meaning take a multiplication and then raise that as a whole group to a power. The result of that looks a little bit like the distributive property, but it's not. Both of the factors inside the exponential expression do receive the exponent, but it's not really the distributive property, although that's kind of what it looks like. Which means that 3 times 2 to the 5th, rather than making that 6 to the 5th, we could make that 3 to the 5th times 2 to the 5th. And we could be done right there in terms of rewriting this. 3 to the 5th is a large number, I think 243. 2 to the 5th is 32. You can multiply those out, and you get the same thing as if you multiplied 6 by itself 5 times, but that's not what we're looking at here. Finally, we have a power of a quotient, which is once again a division or a fraction being raised to a power. One thing that you're able to do is, like with the power of a product, do something that resembles a distributive property and rewrite it so both the numerator and denominator receive the exponent. So here we have 3 over 2 to the 5th. That can just be rewritten as 3 to the 5th over 2 to the 5th. Now, one thing to keep in mind here is that you cannot reduce this. You cannot do anything where you do 3 over 2 to the 0th or to the 1st. The difference here is that these two bases are different. 3 does not equal 2, so we can't use the property we discussed on the other page where you subtract the exponents. That's not what's going to happen here. This would just be your final answer, 3 to the 5th over 2 to the 5th. You could expand them out, but that's not what we're investigating here. Alright, so let's just take a look at a word problem that we can use the properties of exponents to solve. We're talking first about a jellyfish that emits about 1.25 times 10 to the 8th particles of light, or photons, in 6.25 times 10 to the negative 4th seconds. How many photons does the jellyfish emit each second? We're going to write our answer in both scientific notation and in standard form. If we were to write out both of those numbers and do the calculations, it would be a large, cumbersome task, but we can use the properties of exponents to get done what we need to do. Since we're looking to figure out how many photons the jellyfish emits each second, we just set up a fraction that is the particles of light emitted divided by the number of seconds that it takes to emit that amount of light. So you can see that I have 1.25 times 10 to the 8th divided by 6.25 times 10 to the 4th. Now, when I'm trying to simplify this fraction, I can split things up and just take the first two pieces and the second two pieces of each part, the numerator and the denominator, and set it up into two different fractions. So we're going to have 1.25 over 6.25, and then we're going to be multiplying that by 10 to the 8th over 10 to the negative 4th. Now with each of these fractions, I just reduce each one. 1.25 divided by 6.25 using a calculator or long division gives me 0.2. And then I'm going to be able to write my scientific notation here using the fact that I have two exponents, 8 and negative 4, as a quotient of powers where the base is the same. Both bases are 10. So I'm going to get times 10 to some power. That power is going to come from taking my two exponents previously and subtracting them. So I'm looking at 8 minus negative 4, which is the same thing as 8 plus 4, which is 12. So I'm looking at 0.2 times 10 to the 12th. Now that's not technically in scientific notation. For it to be in scientific notation, I actually have to have the 2 to the left of the decimal point, 2 point. You can put zeros in there depending on significant digits or not. We might have them, we might not. So it seems from this problem we have 3 significant digits, so I'll put 3 in there, 2.00. And then because I moved the decimal point to the right, I'm actually going to decrease my exponent from 12 to 11. That is now in correct scientific notation, so maybe I can put a label on that of photons per second. That's a ton of photons. To write out the number, we would just, in standard form, we'd write 2 times 10 to the 11th. That's going to be a 2 followed by 11 zeros. And then just kind of figuring out where the groups of 3 are here. So that's going to be the equivalent of 200 billion photons per second, which is quite a few. It's a lot of light being emitted from this jellyfish.